Hi everyone, and welcome to this week's edition of Water Talks. My name is Ryan Brown. I'm a systems engineer with Innovyze. Been here for about 2 years, but have a background in stormwater engineering and that type of thing. I have with me Jessica Jeffries, who's the product manager for InfoDrainage. If you want to introduce yourself.
Thanks, Ryan. I'm Jessica Jeffries. As Ryan mentioned, I'm a product manager here at Innovyze, looking after our drainage design products, primarily InfoDrainage. Been with Innovyze for nearly 15 years now, working in drainage design and with our flood modeling products a little bit as well, and excited to chat with you guys today and hear your questions.
Yeah. So yeah, if you haven't been to one of these before, it's pretty simple. There is a little box where you can ask questions, and this is kind of more or less an informal type of setup. So feel free to ask questions throughout the presentation, and we'll try to get to them as they come in. If you don't know, we have a few other water talks that are coming up. One involving asset management and one involving calibration of hydraulic water distribution models. So feel free to log on to our website and sign up for those. Today we're going to talk about some of the BMPs and more or less like green infrastructure, just looking at a different way of really approaching drainage design and hopefully ways that you can use InfoDrainage to be able to help streamline some of those things. So in the typical and traditional design, you can see in the background, this is an example of just a dry pond. Most of the time it comes down to being either a dry pond or a wet pond, depending on what part of the country you're in, whether you're near the coast or in the inland. And really the general idea is just to match peak flows. So we as we add impervious areas to different parcels and things like that, being able to limit the amount of flooding that might occur during a typical maybe 10-year or 25-year event. And then other than that, not really mitigating much. Low impact drainage design, this is a kind of an example of a bioretention cell. And really there's multiple benefits. It's not just about reaching existing flows for different storm events and things like that. These can include improving the quality as well as the quantity, different evapotranspiration types of benefits. I can also add a lot of amenity. Citizens in the area certainly benefit from nice looking features rather than a dingy old dry pond or something like that. And then also increasing the biodiversity, bringing in pollinators and different species and habitats for them to live in, as well as groundwater recharge, becoming more and more important as we deplete those resources as we're needing that for potable water, and then also water reuse and being able to use stormwater to help water our landscaping rather than using potable water for those. So some of the common terms, just to for anyone kind of new to the subject, there's many different ones: LID, low impact design, GI being green infrastructure, as well as SEMs and BMPs, and then also some of the ones used over in the UK, SUDS. You can see that in some of our softwares. So that's just another term they use for LID, and then also water sensitive urban design. So the general criteria definitely varies by state. If you do a Google search, you can come up with any number of different stormwater manuals, each for each state. But really the intention is the same between all of these, and it's to really clean up the water before discharging it into into different waterways. And the idea really is to not only match the hydraulic conditions of the existing condition, but also the hydrologic condition by using different natural flow paths, eliminating curb and gutter, those types of traditional designs, and then also treating the water quality volume, or that first flush where I forgot the statistics on it, but it's, you know, a very high percentage of the overall contaminants that are in stormwater, being able to treat that or eliminate it from being discharged into a lake can certainly clean up things um, before they become a problem. So some of the examples, Bioretention Cell, and these can include, this is a profile or a profile view of one. They can include an internal water storage zone to help with denitrification and further eliminate nitrogen from the runoff. Also infiltration swale, basically like a traditional swale, but with a trench underneath it to be able to infiltrate the water instead of just straight discharging it. There's also stormwater or constructed wetlands, which are, the idea is just to replicate a natural wetland system. Also permeable pavement, being able to take advantage of the space that's underneath something that would normally be an impervious surface, and instead letting that water infiltrate into it. Also green roofs to be able to kind of slow that peak before it becomes a problem. Not so much for water quality necessarily, but being able to mimic the natural hydrology of an area. Also rainwater harvesting, being able to collect the runoff into a cistern, and I think most of the time it's used for irrigating landscapes and things like that, but there certainly are cases where it's used to service toilets, as well as being able to use it as a car wash or a truck wash. And then there's also proprietary devices. These can range from like the one pictured here, which is more or less a bioretention cell within a box. So as water comes in there, it treats it just like a bioretention cell would. So really, I think, and this is something that's honestly kind of new to me that I've been seeing more and more recently, is to really rethink the idea of building drainage design. And in these normal conventional controls, you know, we have one or two spots on a parcel that's really dedicated to be able to treat the peak existing condition and get that down to an existing condition. Instead, with the low impact design, it's really decentralizing the treatment and being able to almost create little micro sheds of water treatment rather than centralizing something at results at one spot. And you know, when I first started looking into this, it was always this condition of, well, we'd really like there to be some green infrastructure, so, you know, take a look at it. And so as a consultant, I would just, you know, look at the area that was kind of dedicated for that traditional design and see if I could fit in a bioretention cell, see if I could treat it as far as the quantity and get some of those quality requirements out of it. And very often I wasn't able to fit anything because the size of the bioretention had to be so much larger than a traditional dry pond. So really rethinking how we're approaching the design is I think going to be the key in terms of being able to um, really use green infrastructure in a attainable way, I guess. So there's plenty of opposition to it. One of them being it's too expensive. And just doing like a simple Google search on it, you know, there's something about, yes, it's going to be more expensive, but there's also some other benefits that aren't taken into count necessarily with a lot of these. And a simple Google search will come up with these, like, quote unquote, the real cost of green infrastructure and what that means as far as being able to clean up and being able to not have so many pollutants within your waterways. There's tremendous benefit there to a city, not to mention numbers of grants and other things from different organizations to be able to help mitigate some of those costs as well. And again, it's really more than just a stormwater retention. It's about the climate resiliency parts of it, the carbon sequestration that you can achieve by having more plants within your city, increasing the biodiversity and creating those new habitats for animals to live in. As we all know, things are a part of an ecosystem, and one impact to an animal group is certainly going to have reciprocating occurrences for other parts of the biosystem, as well as enhancing the water, of course, and then also the air quality, being able to, again, pull in CO2 from different sources, and then also increasing the infiltration and therefore decreasing some of the flood risk. Also, the public health aspect of it, being able to create natural areas for people to go and enjoy and have some areas to recreate in, which leads, of course, to a quality of life and the reduced heat island effect by being able to not have as much, by being able to create shade in some of those areas and reducing that heat island effect. Some other ones, there's also just environmental and then also economic benefits. The same thing with, like, the quality of life and being able to attract different populations to your city and have them be more enjoyable there. And they're certainly adaptable to different situations as far as being able to rethink that green infrastructure and or rethink the drainage design in favor of green infrastructure. It's definitely an investment up front to be able to reduce costly damage in the future. Some of those things of decreasing the amount of flood risk by increasing the infiltration, and then also more and more we're seeing some increased regulations from different states and municipalities, as well as subsidies and grants to really help with the delivery of it. And at this point, I was going to switch it over to Jess. I did see we have some questions come in. I don't know if you took a look at those, Jess, and there's some we can answer.
Yeah, there was one. Let me just get my screen showing the right screen. 1 second.
Yeah, I was having trouble with that too. You got to right click on the, yeah, there we go.
There we go. Okay. Yes, we had a question come in, and you've sort of answered it, I think, in those last couple of slides about public perception of vegetation in water. Is that, sorry, the question field's now gone really small. Now I'm the presenter. Yeah, two similar questions, but essentially about vegetation potentially reducing the capacity, getting mown down accidentally, being seen as negative in many ways. Do we have any information on cost savings and so on? And I think, as Ryan's mentioned, it's about being able to demonstrate the additional benefits and focusing less just on the water quantity. Although having infiltration and having evapotranspiration gains that come with vegetation, I think selling the whole picture of what green infrastructure brings to particularly urban environments and how it can add those extra benefits is a really important part of it as well. Anything else, Ryan?
Certainly, and I mean some of these things as far as public perception of ponding water, and that's going to lead to mosquitoes or other kinds of um, bad things, I guess you could say. Um, there's, I don't know of any studies off the top of my head. I'm trying to think back. I know we talked about it a lot when I was in school. Um, and I'd have to do some digging, and I might do some while we're chatting right here. But generally, from what I remember, it was always a healthy ecosystem isn't going to have those problems. That yes, you might have some mosquito breeding and things like that, but there's also frogs and things that come with that eat those mosquitoes, and so they don't become so much of a problem. But yes, there's certainly some of those kinds of things. Um, as far as flood safety for um, residential sites and stuff like that, um, I would argue it's up to the designer to be able to have different structures in place and things like that to be able to um, bypass some of those higher flow events and things like that. Um, from what I've seen and heard, there's generally not a problem with flooding or problems with houses and things like that, but I can certainly see where that's a concern.
Yeah, I think what I've seen previously is where you have those really big detention basins, at the downstream end of the site. I tend to refer to them as pipe to pond solutions. There can be concerns around safety and water in residential sites, but where you see the green infrastructure integrated, a bit like your example plan drawing, Ryan, where it's throughout the development, you have much smaller bodies of water that where they are, they're adding amenity value and don't tend to have as many problems with actually the drainage being seen as a negative. It actually starts to be seen as something that contributes, and in some cases can even increase the value of the residential development, because it's a nice environment. People want to live near water often. So yeah, that more distributed approach dealing with the water at source, I think, helps to mitigate some of those risks and perceived risks.
For sure. Looks like we have a few other questions, like being able to model, um, will modeling GI structures. Yeah, they will be covered somewhat in the webinar for sure. So we'll certainly get to that. And then one more question on how is it LID modeling different in InfoDrainage and being able to import SWIM models and things like that. We'll certainly get to some of that stuff as well. It is fairly similar from what I remember. InfoDrainage does use a SWIM engine, so some of those things are similar, but of course the interface and things like that are, in my opinion, much easier to understand.
Yeah.
So I think we can go on from here.
Okay, sounds good. So thinking about some of the other opposition then, and why green infrastructure maybe hasn't been used as widely up till now. We sometimes hear that it's too hard to design. A couple of questions there on the modelling side of it, and the perception that it's too complicated, and meeting the water quantity requirements with a green infrastructure solution is too difficult. And we've really had that in mind with some of the challenges that are being faced in drainage design. We're well aware that optimum sizing is really important, because an oversized structure is going to result in an increased end cost for clients, and obviously an undersized structure is potentially going to end in disaster. So we've got built-in tools that can help to size those structures, calculators, and then of course, you know, all important sort of final analysis to check how they're behaving in different circumstances. We've also seen that the perception can be that the green infrastructure can't be designed together with the rest of the drainage, the pipes and manholes and so on that maybe connect these solutions up. And that's not the case. All those different structures can be included in one design, and it's actually really important to include them in the same design so we can see how they link to each other, how water flows throughout the whole drainage solution, and avoiding conflict with nature, with the natural environment that's already there, making the best of the existing ground and delivering something that actually enhances the environment is really important as well. So we've looked at all these challenges and put solutions in place to help you meet those within the software so that you can represent all of the green infrastructure aspects, but you also still have a good design process that's going to give you an optimum size structure, because ultimately budget's going to continue to be important and you're still going to have regulatory requirements to meet at the end of it. So in terms of how that looks in the software, one of the ways in which we're trying to bring drainage more to the forefront of design as a whole. So it can often be left till late in the process, but we're seeing more and more that where we have the opportunity to actually look at the ground before the design is laid out, we can use the existing flow paths that exist on the site. We can use the existing ponding areas that exist to better inform the spatial planning elements. So this can easily be done just with a simple surface model. We use what we call the deluge function and analyze where would the water naturally go here. Let's work with that, and our drainage design is going to be a lot easier and not conflict with nature as much. The background image here is not essential, just enhances how we interpret that that deluge flow paths and ponding areas that we get at the end of it. And then we also have placed this optimized design process where we are designing graphically and where we're using the automatic sizing tools as much as possible, using templates as well, so that we can quickly lay out different kinds of green infrastructure solutions. So here we've got a template of our swale. It's pre-set up with a 1-in-4 side slope. We're able to put in the exact locations of those inlets and outlets. We can have our low level under drain, our high level overflow, connecting multiple different areas here. And we can even have those areas draining in a lateral way. So if they're flowing into the side of the swale, that can be accommodated as well. And where we actually have the information, we can use the exact layout of these systems so that we can graphically see how much space they're going to take up. And not only does this help us understand whether they're going to fit on the site, but also helps us then to communicate the additional benefits that those green infrastructure solutions have. Because if we can show that they're spread throughout the site, if we can show that, for example, in a residential development, you know, multiple houses are going to benefit from having sight of these solutions, which can be quite attractive, then this can make it easier to communicate, even if under the hood they're actually more complicated. And going into a bit more detail then in terms of the hydraulic representation, what we want you to be able to do is be confident that the information you've put into your design is going to behave as close to reality as possible. So representing the, for example, in these swale type structures with a trench underneath, you can actually see on the profile view that we have a grassy swale above ground, that we have a trench under the ground, and they're dealt with differently. And actually the filtration through those layers in the underground trench is accounted for in the analysis. We can see that that's happening because we've actually got two different water levels appearing here in our profile view. So if the water takes a while to flow through from the top part to the bottom part, we're going to see that on our profile and take account of the different materials in them. So we've got the visual tools to help communicate them with our regulatory authorities, that actually they can be confident in a green infrastructure design. And then as well as those graphical tools, we also have the option to compare different phases. So we may want to look at a more typical pipe to pond approach, and we may want to compare that to if we have a distributed green infrastructure approach, and see which of our approaches gives us the outcomes we're looking for in terms of reduction in total runoff at various different return periods. So we can see whether that green infrastructure design offers a benefit from a water quantity point of view or from a water quality view. We could even compare different types of BMPs, see which one is going to give us the best solution to help inform, and help give us confidence that even though we're working with something that's relatively new, we're still getting the outcomes we need to meet those regulatory requirements, get consent and get approval.
And,
So,
if you don't
sorry,
mind me
Ryan.
interrupting, that just made me think about something, seeing some of those reports and stuff like that. So, and correct me if I'm wrong, but in the UK, you have to look at a variety of different storm events for both the length of the storm as well as the return period. And I always found that really, really fascinating, and I wish we would do more of that type of thing here, because often we're just looking at one or two storms and not realizing the impact of something that either might be more extreme or might be more realistic in what's actually falling from the sky.
Yeah, that's right. Typically, we look at storms in the UK ranging from 15 minutes up to 40 minutes, which is a day, although we have actually gone longer in some cases. And what we see is that the more retention there is on site, the generally the longer storm durations tend to become the critical event or the worst case event. So it's really important the way the design storms are run in the UK, that they are all considered, because you might not capture the worst case if you're not looking at all those storms. I don't remember exactly how the SES storms, for example, are formed, whether there's some kind of composite.
Yeah, so we have four different types of distribution,
Yeah,
depending on where you're located in the country. Most
yeah,
of them are type 2 distributions, but generally it's based on the NOAA Atlas 14 map and just the frequencies and
yeah,
intensities associated with different
yeah.
parts of the country.
But I guess the thing that that is important to remember is just that the the green infrastructure elements are going to behave, going to behave a bit differently because they do tend to retain water. Often they're designed to retain water. Those, sand and soil
Yeah,
media often holds the water back, and that can really add an additional benefit in protecting the downstream part of the site, or the downstream catchment. So if we don't do a full analysis, we don't necessarily see those benefits, and if we're not actually representing that media in our hydraulic modeling tool, then we're not going to be able to demonstrate the benefits as
yeah,
easily.
and I think you're getting to it, but the concept of eliminating the runoff from a catchment has been getting more and more traction as far as
Yeah.
protecting the water quality. I think that has certainly caught on in the past couple of years here in North Carolina. But the kind of thinking behind it was something like, I think 90% of all storm events during the course of a year are a 2-year or lower. So if we can
Yeah.
infiltrate all the water from a 2-year event, it can certainly give us a lot of benefit.
Yeah, absolutely. I moved that, so it's up next.
Oh, okay,
Um,
sorry.
that's good. So, Ryan set me up to talk about some of the water quality requirements. And what we often see is that in order to demonstrate a good water quality outcome, we can actually take a water quantity approach. So Ryan mentioned runoff reduction volumes. If we can show that we're dealing with the total volume that's received from a small rainfall event, like a 1 or 2 year, maybe a 1-inch storm, and that volume of water is captured by our LIDs, then we can actually infer that we're dealing with the water quality, because typically those short sort of more frequent rainfall events are going to wash the worst of the pollutants off of our landscapes. Where we have more extreme events, generally any pollutants in that water, if it is just stormwater, unless we have obviously some sewer overflows happening, but generally the pollutants are going to be diluted down to concentrations where they're not as much of a concern. So here what we're looking at is, you can see similar design. We've got an infiltration trench in this scenario, and we can actually use the built-in calculators to check whether that trench is going to handle the volume of the upstream catchment for a runoff reduction event, for a water quality event. So we can set the calculator up as to what we would like to change if that needs to increase. 2 options for the method. We've got the runoff reduction method there as per the New York State Design Manual and the Atlanta Stormwater Manual, among others, and there's more information in the help file on that. And then we've just put in 1 inch of rainfall, and it tells us that the outcome is a failure. So what it's done is it's taken the catchments upstream and calculated the volume generated off those catchments, looked at the stormwater control volume as it stands currently, and seen that it's not actually large enough. When we click OK, it updates, and then we can apply that and see on the plan view that that will increase the size. We said length and width, so it slightly increases the size of that infiltration trench in order to meet the runoff reduction volume. And having that built in just means you can do those checks as you go, and then you can actually run one for the whole site at the downstream end to check you've met all those requirements. We can also there, just showing that on the inlet, could then set up a capacity restriction so that our extreme events could bypass this, in order that we don't get the LID scoured out, say, by a very extreme rainfall event. So you've got options there just to help make those sizing easier to start with, that you can then check with the full hydraulic analysis at the end. Equally, you may need to or want to go into a bit more detail on the pollution removal. So if you've got regulatory requirements that require you to actually, rather than just look at the runoff volume, actually demonstrate what percentage removal of pollution we have from the site, there's multiple options in the software to do that as well. So here on our inflow areas, our catchments, we've set up 2 pollutants, total suspended solids and total phosphorus with a concentration. But we could be looking at a much wider range of pollutants. It's completely in the hands of the user how many pollutants they want to assess. And then within our LIDs, we can choose one of 2 methods and set up actually how much treatment, if you like, these are going to give. So here we've got the total suspended solids being reduced by 60% in the trench and the phosphorus by 40%. The percentage removal method is fairly simple. We also have a first order decay method. And with either method, we can keep a background concentration. So we might say, for example, we know that even whatever happens, we're not going to reduce all of the total suspended solids. So we put that background concentration in. The first order decay method, you can see here again, there's a little calculator just to help with some of those parameters, but it works on residence time. So we're putting in like a half-life here of an hour, which then allows it to see how the pollutants reduce over time. So depending how long the water spends in that pond is going to depend how much pollutant gets removed. Again, some more information in the help on that method. And then we can look at the results in a bit more detail, see that here, you know, the concentration's increased as we've had more inflow, but we are getting an overall reduction of 70 to 80% of both of those pollutants by that bioretention basin. So you've got the options to take a water quantity or a more detailed pollution removal approach.
And I think just something worth mentioning, just because I know that type of thing, that type of analysis might not be required by a lot of places. A lot of the regulations that I've seen, you kind of just size it based on whatever their you know, rules or equations or whatever's published in their stormwater manuals. But at the same time, I really feel like this could really benefit in terms of being able to see during larger events how are things going to perform, how are the pollutants going to be reduced during some of those higher events. So
Yeah, exactly. Particularly if we are bypassing the
exactly, yeah,
you know, the LIDs in the higher events.
right.
Okay, I know there's some more questions coming in, so I
Yeah,
will.
this is a good. Do you want to speed through, or do you want to answer some of these
Yeah,
questions real
shall
quick?
I speed through and then
Sure.
we can come back to the question. So another thing comes up that it can be too hard to get approval, and I think some of the things we've already shown around being able to show visually what's happening can really help, particularly where maybe you've got stakeholders that aren't experts, being able to show them the plan and also those profile views can help to give them confidence. But it can also make approval easier in many ways because often green infrastructure is required and maybe some people are finding it difficult to do. So being able to show that you're including it can be a real advantage. So I will speed through that and just show as well some of the customized reporting to help just with general drainage design approvals, but also where we're including green infrastructure. We can actually generate an audit report that will cover all sorts of aspects in your design: pipes, manholes, discharge rates, can comparing pre and post development discharge rates, for example, and flag where we've got passes and fails based on the parameters you've put in. That can be saved as a template and reused, and so making it easier for you to keep submitting to the same regulatory authority if you work in one area, or save multiple templates if you're working in multiple areas. There's also some tools when you're reviewing the failures to update those to comply. So just helping to speed up that the point at which you can be sure you're going to get approval and meet the requirements. That audit report is part of the wider reporting, which again can be templated so that you can include all the details you need to about those LIDs, about every aspect of the design, and demonstrate to whoever needs to look at your design, water utility or council or authority that's giving consent, that they can be confident in the design structure itself. And then finally, just looking at in those specific cases where we're comparing, say, a pre-development condition and a post-development condition, we can set those up. We looked at some of the optioneering phase management earlier for comparing, say, two different green infrastructure solutions, but we could equally use that to demonstrate that we have met the pre-development conditions. So what was, if it was a greenfield site, for example, what was the runoff, and then with our designed solution, what is the situation after we've developed the site and put in our drainage solution. We can use the comparison report here to compare between those different phases and show that we are actually not exceeding the runoff rates and the runoff volumes. So, for example, we've got the existing discharge and the post-development discharge as well there. Okay, whiz through that last bit, so we've got time for some of the
that's
questions.
good. And just with those like auditing tools and validation tools, I've really liked those. I remember lots of just visually checking velocities and cover depths and things like that, so makes it easier there. So the first question I was going to go to up at the top here. These are two questions by the same person that are kind of along the same lines, but as far as bringing in models or converting models from InfoWorks, converting transfer to InfoDrainage, and then also asking about some of the features, will they be available in InfoWorks ICM? I guess to kind of answer this question, there's not a good way to go back from ICM into InfoDrainage, but there is an excellent way of going from InfoDrainage into ICM. We've recently added in the capability to import models, and so my envisioning for this would be the design consultant engineer would be able to design all their facilities and infrastructure within InfoDrainage, and then just give that to the client as a submittable, and they can import that into their larger master plan model. I think the important thing to kind of distinguish and remember between ICM and InfoDrainage is ICM is very much a analytical tool. It's not necessarily intended for design work, versus InfoDrainage is very, very much a design tool. And this kind of goes into some of the other questions I'm seeing here about being able to import and export line work from GIS and CAD. It definitely has some very, very good routines for doing that, being able to export plan views, profile views with a lot of the labels, as well as XMLs for bringing into a Civil 3D pipe network with all the connectivity and everything.
Yeah, just to add to that, the catchment areas and the outlines of the LIDs themselves can also be imported from GIS or from CAD. The pipes and manholes, if if they were part of an existing database in GIS, they could be imported. And we've actually, I think, at least internally, we've used the Open Data Import Center in ICM just in terms of CSV exports from ICM. Say, it's a little more onerous than going the other way where we've got the dedicated importer, but you can import from CSV, Excel, GIS into InfoDrainage. So it's pretty flexible in terms of what you can get in. It's certainly not a case of starting again.
Yeah. Some other questions about modeling unsaturated groundwater flow. I'm going to say like the basic answer would probably be no, but we certainly have, different infiltration losses methods. So like if you wanted to use green amped or something like that, you could certainly do that. But we don't have like a groundwater model like I guess some of the
No,
other softwares out there.
no, not groundwater.
And then another question, it looks like it was probably in reference to the deluge thing that Jess showed, which was that it didn't seem like we were using elevation data, but there was a ground model in there. So it's basically, dropping, I guess, what was it, like 2 inches of water or something over an
Yeah.
area and just kind of like letting it flow and seeing where it goes into. We got another question about optimizing this for the Canadian market or American standards and manuals. So the other thing that I really like about InfoDrainage is it has a regionalization option. So how it's different than ICM. ICM has a lot of, because it is used all over the world as a tool, it's got a lot of things that you might not use or know about. Well, InfoDrainage, you're able to kind of take out the things that you might not use. So if you're in the US, it's going to recognize that your computer is in the US and going to automatically assign you to the US. There's not one specifically for Canada from what I remember, but you can change the units to metric if you are using that. And then I should also mention that the different templates and things that you were showing, Jess, the bioretention cells, the infiltration trenches, and all that kind of stuff. Those are truly just templates that come with the software, but you can add as many templates as you'd like. So depending on the jurisdiction you're working in, their standards, you can set up those different templates to be able to meet those as well. Do you want to add anything, Jess?
No, I don't think so. As
Okay.
you've said, like the templates help, the regionalization helps because it can sort of filter out what's less needed. So
Yeah.
no, that's good.
So this is more of a, I guess, maybe philosophical question about LIDs, but where do LIDs stand for a larger storm? It certainly can help with some of the peak, but are they discouraged for larger, controlling larger events? I think there's a couple of things going on there that if you are using this to be able, you wouldn't really want to use this for return periods above just a couple of years or something like that. As I mentioned before, a lot of the lower level events, that's going to capture a majority of your storms. If you did need to mitigate against a 50-year or greater return period, you probably need to use something more traditional in like a train type of system to be able to capture that first flush or something like that within your green infrastructure, and then capture the peak flow in something larger.
Yeah, I think we've seen in the UK some good, some good sample sites where either they make use of sort of bypassing the smaller structures in a larger event and have some kind of storage downstream, or actually if you've designed those green infrastructure elements to only take a small area each, then you don't have as much risk of, you know, scour or something in a really high rainfall event, or putting in protection, say, around the inlet, so that if there is a really extreme event, you know, there's not going to be any damage. But ultimately, if they're sized to take a smaller catchment, then they're not going to receive as much flow as well. So
That's
I,
a good point.
I think there have been some, you know, some sample sites where they have been tested and used for higher retemperate, because certainly in the UK, all the drainage would typically have to have no flooding for a 30-year retemperate. So,
Wow.
and yeah, even tested up to 100-year, just to see where those overland flow paths go.
Yeah, but another good reason to use that like decentralized approach.
Yeah.
It lowers the risk of blowing out and all those other things. Before I forget, I did want to mention I did do a little bit of looking around on some of the stuff, but the mosquito control and the perception and stuff like that, I posted in the chat just a link to suggestions for mosquito control, and I think the summary of it is, if there's going to be ponding water somewhere, there's likely going to be mosquitoes, and a lot of the infiltration types of LIDs, things like the bioretentions and the infiltration trenches. Often there's just not a problem with those because there's not a lot of ponding water, and especially if you're maintaining it properly. And then also, often those kinds of facilities will treat runoff from roads and things like that, and it'll include oils and other things that make it really inhospitable for mosquitoes to breed. But also mentioning in that article that the creating these environments will often create really good environments for the mosquito predators for helping keep those populations down. Moving on to some of the other questions, being able to calibrate the decay coefficient. From what I understand, the best way of handling some of that stuff is looking up, published scientific results. I would guess you could calibrate it. I don't know that you would do that necessarily in InfoDrainage, but doing like bench studies and stuff like that.
Yeah, there's a lack, I would say, globally of data on actual performance, or at least there's kind of a lack of a collected set of published data, but it does exist. It's just a case of finding it, and you know, whilst it's a bit more scattered, we don't tend to necessarily say what the exact value should be. But I know, for example, in Australia, there's a wealth of knowledge where they've been implementing, they use the term water sensitive urban design, where they've been implementing these types of structures for a really long time, and we're starting to see that more and more around the world as well. There was a question about cities, I think, that have changed their stormwater standards earlier on, where they've implemented a lot of green infrastructure. I don't know whether they've specifically changed their stormwater standards, but I know that Portland, Oregon is known kind of across the US and even across the world as being a leader. They've certainly been implementing green infrastructure for a long time, and if you go there and sort of walk around, you actually notice things. Well, certainly I did, but you know, I guess I look out for that sort of stuff. Yeah, you notice them. You notice them, and you know, probably to lots of people it just looks like some nice planting, but actually you realize it's part of the stormwater solution, and just shows how it can be integrated into a city landscape without, you know, the taking up too much space kind of perception.
Yeah, and that kind of goes well into next question I'm seeing about just maintenance and getting a better, I guess, feeling, especially if places are starting out to implement some of these things. And I guess just to add on to some of the stuff you were saying, this is seems like a constantly evolving field. It's relatively new. I think it was the early 90s, so that really a lot of this stuff started coming into practice and doing more research on. So there's definitely changes that occur all the time. But anyway, this one was about maintaining things like a constructed wetland and being able to, you know, how often things need to be flushed or vegetation needs to be removed. I would suggest going to some of these states and leaders as far as, you know, the Portland, Oregon area, and I know the Chesapeake Bay area, which is where a lot of this green infrastructure really started. And then also just a shameless plug for North Carolina, because that's what I'm most familiar with. But there's definitely some great resources with NC State and their biological and agricultural engineering department. Lots of good information as far as what are the best ways to maintain things. I would guess for you know, kind of flushing out everything, you might get an extreme event or something like that, like a 25 or 50-year storm that could do some of that maintenance for you. But those types of things.
Yeah, I think as well, sometimes some of the perception has been that, you know, maintenance of green infrastructure isn't understood or is more onerous. But of course, you know, infrastructure, even that's not green, needs maintenance as well. So we have to just make sure that we're comparing, you know, like with like when we're saying it's harder to maintain or it's more costly and that sort of thing. And
Right.
actually, there's been some success, I know, with you know, shared maintenance, if you like. If there's a grassy swale next to some kind of public area that is grass as well, then potentially it's almost a no-cost maintenance just to cut that grass a couple of times a year or whatever it needs doing. So just a case of looking for the opportunities, I think, with that sort of thing.
For sure. This next question I might need a little more clarification on what you're asking, but which approach is used for designing storm sewer systems? If you're asking about the engine that InfoDrainage uses, it does use a version of the EPA SWIM model. We've modified it and made some improvements to it, but for the most part, it is the same. And that's what it uses for, you know, sizing the capacity and all that kind of stuff.
Yeah, there's actually, we often see engineers use a bit of a two-step approach, because sometimes using the rational method, for example, to size pipe work is maybe a first step. That's like a static calculation in terms of calculating peak flow, and that can be done as a separate and standalone activity if that's all the requirements are, as is still the case in some areas. And running through a wizard, size all the pipes to the rational method. Usually
Yeah.
what then happens is then the green infrastructure is integrated, or the other storage elements, the more complex flow controls and so on. And then we run the full hydraulic analysis and test for those different rainfall events. So both of those options are available. They can be used as a two-step process or either of them individually. Just depends what your exact workflow is.
Yeah, and just to finish up on that note, it does look like that was the question behind it. Um, there's certainly modification as far as optimization goes. I thought there was still some optimization that it would, potentially run a little faster than swim, like just a traditional swim model, but I think you would know better, Jess.
Yeah, I forget all of the engine modifications. The ones I guess that are the the most important for InfoDrainage are in relation to the implementation of they're called stormwater controls in the software interface, but the BMPs, that's been um, that's a hydraulic analysis approach to those structures that isn't available in the EPA swim engine. Um, the then I think the calculators, the wizard for the pipe sizing and so on are kind of the other pieces to optimize the actual sizing.
Well, I think we've gotten to um, most, if not all, the questions, and we are about out of time, so it seems like a good place to stop. I appreciate everyone joining and tons of engagement. That was really, really great. So we'll see you next time.
Thanks all.